everyone. My name is Bobin. I'm from Polygon, and we're here today recording another episode of the ZK Whiteboard Sessions. And here with me today is Barry Whitehat from the Ethereum Foundation, and we will be talking about ZK-rollups. So I guess the first question, Barry, in general, what is a rollup and why do we need it?
Right. So a rollup is a way to scale blockchain.
Okay.
And we need it because because blockchains are really, the amount of transactions they include is quite low. So like the way that blockchains work is that there's always this commitment, there's always this state. And the state is basically like how much money everybody has. So this is like one person, this is another person, this person has like 10 and this person has like 9.
Yep.
And then every time we make a new block, we have a state transition, right? And we move from this state to a new state. So let's see what the new state looks like. Okay, so this is the new state, and we updated these two leaves. So what's the balance of these two leaves? Okay, so this leaf, let's call this one 9, and let's call this other one 10. Okay?
Yep.
So basically what's happening here is like this user is sending one something to this other user. And this is called a state transition. And like the way that blockchains work is that this state transition is validated by all of the nodes. So there's many observers, and they all observe this state transition. And when you see the state transition, you say, oh, this is a correct state transition.
And when you say observe, they actually, I think, re-execute the transactions to get the same exact state transition.
Exactly.
Okay.
Yeah. So the way that a blockchain works is that we have this state transition. Everybody is observing and confirming that it's correct. If someone presents an invalid state transition, all the users will ignore it.
Yep.
All the users will be like, oh, that's not correct. I don't want to be part of that. I want to be part of the correct one. And this is how blockchains work, and this is why they're secure. So they're secure because everyone is checking. But like the problem is that like when we have a state transition and we have many users to check, we want to make the state transition as simple as possible so that we maximize the number of users that can check. And like the way that we do that is that we just reduce the number of transactions that we have. Here we have just one transaction, and this makes it easy for us to validate.
Yeah. So if we wanted to put 1 million transactions into a block, some participants in the network would just not be able to keep up to validate all of them.
Exactly. Yeah. But like what we do with rollup is we want to put 1 million transactions into a block. So let's talk about how we do that.
Yeah.
So with a rollup, we have the same situation, but instead of having everybody check, we have something that guarantees the validity. This can be a ZKP, or it can be a fraud proof.
Okay.
And basically what happens is that the ZKP makes sure that all of these transactions were done correctly. And this gives us our validity guarantee. But we also need to have a data availability guarantee. Because if users don't know the new state of the system, they won't be able to make more transactions. They won't be able to withdraw. And like these are two important issues. So in order to guarantee that our data is available, we make sure that our proof also comes with a representation of all the transactions that happen. So let's take an example. Here we have a transaction where this person sent $1 to this person. So what's the simplest representation of that? The simplest representation of that is the from, and the amount that was transferred, right? So we say, okay, so from user 0 to user 1, we transferred 1. Okay? And with that information and the previous state, you're able to calculate the new state.
Makes sense.
Yeah. So
now, usually when you send transactions, you sign them, right? There is also a signature involved. And this is when we are talking about L1s. On L2, is there a signature as well, like when we're talking about rollups?
Yes. So in the context of rollups, it's really important that users consent to this transaction. Because on layer 1, everyone signs to say, oh, I want to send this much money from me to this other person. So it's important to do that on layer 2 as well. So, and we do that exactly the same way. We have signatures. And like, yeah, we have signatures, and we use those signatures for users to consent to say that, oh, I want to send one token from me to this other person.
Makes sense. Okay, so to kind of like make sure I understood everything, in a ZK-rollup, there is a separate state. So we still have the L1 state, which is separate, and then there is an L2 state, which is now this represents it. And then the validity aspect it proves that the L2 state was transitioned correctly.
Yes.
So I'm just trying to understand a bit more about like interaction between L1 and L2. So like, let's say we have an L1 smart contract or something. Like, what do we actually push to L1 when we have a transition on L2?
Okay, so let's take this example and let's draw the smart contract that's used to execute this example. So we end up with 2 layers. So we have layer 1. This is the blockchain that already exists. This is the one that we talked about earlier, where everyone is validating every single state transition.
Yep.
This is the one that we talked about that's very few transactions per second. And inside of this, we make a second layer. We make a smart contract. This smart contract makes our layer 2. And basically what this smart contract does is it accepts a ZKP.
Or a fraud proof.
Yeah. It accepts and some call data. And like, maybe call data is not the best word. So like, there's different words that are used to describe the minimal representation of the state transition. So like, some people use diff, some people use call data. What do you think is a good term for this? How about state transition representation?
Let's go with state transition representation.
It's a bit of a mouthful, but let's go for it. Okay, so they put the ZKP, and they also put the state transition representation. They put both of those things into the smart contract, and the smart contract then basically does the following things. Number 1, it verifies the ZKP is correct. This is our validity guarantee. Make sure that, oh yeah, this transition is correct. All of the users consented to this list of transactions. Secondly, it checks that this list of transactions is included in the ZKP. It checks that like the state transition representation is part of the ZKP. That's the second thing that it checks. And the third thing that it does is it remembers the new state. So it used to remember the old state, root. And after we do the state transition, we go to root prime.
Yep.
And the smart contract just says, okay, root prime is our new latest state. And so we have, this is our layer 2. This is our layer 2. And our layer 2 is basically like a contract that tracks the root. Every time we update the root, we give it a ZKP and we give it a state transition representation. And this guarantees validity, and the state transition representation guarantees data availability.
Makes sense. So just to clarify a few things. So the root is the commitment to the state, right? So by kind of like knowing what the root is, we know kind of that there is a state that is a specific state and it cannot be changed very easily, and that when we execute the smart contract and verify this, the root actually changes, right?
Yes.
Why can we just simplify this and just have a root in there as well? Like, what would happen if we don't have the state transition representation? You just have a ZKP and a root. Like,
okay, so let's talk about that. Yeah. So in that context, what would happen is that we remove the state transition representation, and our users who are observing the system would not know this information. If they don't know this information, they wouldn't be able to withdraw, or they wouldn't be able to do another state transition, because this is one state transition, but we're going to do many, many more. Like, the point is that like each of these state transition functions is like a new block. We're processing transactions. When we have more transactions coming, we need to process them. And if we don't know the data, we're not able to do another state transition, and we're not able to withdraw. So that's why the state transition representation is a very important part of the guarantees of rollups.
Makes sense. So while ZKP guarantees that you cannot do invalid transition, there is still somebody who doesn't reveal the state. They can do like valid transitions but hide the actual state, and then it's kind of like you're stuck in that situation where you don't know exactly what the state is.
Exactly. So like it's kind of like a ransom attack.
Yep. Makes sense. And then if we don't put the state transition representation, that is technically not a rollup anymore, right?
Yes.
Okay.
That is correct.
Okay. So rollup, you have to be able to reconstruct the state. And I guess that brings me to a question, like what are the properties of a rollup? Like what do we want to say, like this is a rollup and this is not a rollup? What are the key properties that we want to, or guarantees that we want to ensure?
So what we want to ensure is that like the rollup inherits its security from layer 1. This is the key property of rollup, because let's look at the situation that we have. We have a layer 1 that's very secure because many people are checking it. Many people are being careful about, is this correct? And we want to include more transactions, but we want to have the same security guarantees. So basically what a rollup does is it says, okay, I want to inherit those security guarantees. The two security guarantees are validity and data availability. So we use the fraud proof or the fraud proof for the ZKP to verify the state transition function. And then we use the layer 1 to guarantee the fraud proof, the ZKP is correct, and also to make sure that the data is available. So the key thing about rollups is that we want to inherit our security from layer 1. That's the key property they're trying to achieve.
And I guess by security, we mean maybe a couple of things. The one, our funds cannot be stolen from a rollup. The same kind of applies. And the second one is our transactions cannot get censored, right?
Yes.
I guess we didn't talk about this yet, but I'm curious. So who is actually generating the ZKPs and putting this on L1? Like, is there an entity? Is it one entity? Is it many entities? Like, how does it usually work? And what are the trade-offs of different approaches?
So there are different approaches here. So, like as you said, there's always an entity that needs to create the ZKP. Yeah. So they have like some powerful computer, or maybe not so powerful, depending on the ZK-rollup. And inside this powerful computer, they compute the ZKP, right? They get transactions from the users. Our users are here. Let me draw some users. Yeah. They get transactions from our users, and then they use those transactions to make the ZKP. Finally, they send the ZKP to the layer on the layer 1. The layer 1 then puts the ZKP into the smart contract and produces a layer 2 block. So the entity that makes these proofs it seems like they're quite powerful because they're getting transactions from users and they're putting them on chain. And like we said before, that like one of the things we want to guarantee is that there's censorship resistance here. We want to make sure that like this party isn't able to censor other users.
And by censorship resistance, basically, if I want to get my transaction, if I have the funds in a rollup, I want to be able to make sure my transactions get executed.
Yeah. So this party could theoretically just say, I don't like this user. I'm not going to include their transactions anymore. Right. So right, how can we decide who to be the coordinator? It seems like it's such a powerful position.
Yep.
So there's two approaches to limiting the power of the block producer. And like I recommend that like we take both approaches, but let's talk about them and see.
Yep.
So the first one is to basically say that, okay, let's just make other people who are also able to make ZKPs, who also have a computer, they make their ZKPs. They make their ZKPs, and they send them on chain. And we have this kind of like competition. And the users are then able to decide, I want to send my transactions to this one instead.
Basically, whoever will be willing to process my transaction.
Yeah, exactly. So this is the first step in kind of like preventing this censorship issue.
And this somewhat replicates like a L1 dynamic, right? You have kind of some form of consensus that these guys need to come to before they can send something to, unless maybe there is a race condition if they, I'm guessing there are many ways to like coordinate these guys between themselves, right?
Yes. Yeah, there's many ways for them to be coordinated. One of them is proof of stake. Proof of stake is basically where everyone puts down a deposit and like you trust people, you assign people a right to make a block based upon how big their deposit is. And the reason why this is secure is that basically if this person puts down a deposit, they're losing something. They have like an opportunity cost with that money.
Yep.
And when they receive transactions from users and they don't include them, they're missing out. You know, they could make more by receiving transactions from other users. So that's how proof of stake works. And proof of stake is very secure on layer 1 because on layer 1, if there's some very rich person who is getting the opportunity to make many blocks, and decides, I don't want to make blocks for this user. I'm going to censor this user. I don't care that I'm losing a little bit of money because the amount of money I'm losing is so tiny compared to the size of my stake. It's not, I don't like that user, I'm not going to do it. And if that happens, on layer one, we can have what's called a hard fork to recover. Basically, on layer one, the other participants say, that's not the rules of the system. That's not the properties of blockchain. We're going to change the system so that you don't have that state anymore.
So you bring like a social aspect to this and be able to kind of recover through social means.
Yes.
Yeah.
So on layer one, you can recover from this type of censorship attack via social recovery hard fork.
Yeah.
Unfortunately, this doesn't work on layer two. Because if we were doing the same thing on layer two, and like a certain user and the same attack happened, and we wanted to do a social recovery hard fork, we couldn't do a social recovery hard fork of the layer two. We would have to do one of the layer one. And like historically, it's been very rare for there to be hard forks to recover broken smart contracts. And I think that in the future, it's going to be very, very difficult to do. It's very hard to justify that because it basically means that like everyone has to change their philosophy or everyone has to accept this slight change in order to help this broken thing. So because of that, I think that leader election via proof of stake is not a good mechanism on layer two.
Yeah, because if somebody controls a significant portion of the stake, they can still censor transactions.
Yeah.
Did I understand right? Okay.
Yeah, exactly. So instead of doing this, we can have some other mechanisms. So like we talked earlier about like how on layer one, we want to inherit the security guarantees of layer one. And layer one has very good censorship resistance. So how can we inherit this guarantee? Well, one thing that we could do is we could, let me make a little bit of space here. Mm-hmm. Is that we could add something to our L1, to our rollup. And we could basically make this kind of like forced transaction, right?
Okay.
And
could you explain what it is?
Yes, I can. So let's talk about the context first, okay? Let's say that we're in this situation. This user is being censored, not just by one coordinator, but by all of them. They're running the kind of like the same attack that we discussed earlier. And the layer two, this user is just not able to get their transactions included. So the idea of a forced transaction is that this user could, instead of sending their transactions to the block producers, could send the transaction to the layer one. And because layer one has better censorship resistance guarantees, the transaction can be included the transaction will appear here. Because like layer one's censorship resistance guarantees are very, very strong.
So the logic in the smart contract will actually say you cannot execute the state transition unless you execute this transaction. Is that right?
Yes, okay. That's right. So the next part is that like once a transaction appears here, if any coordinator wants to make a new block, they must include the transactions here. That's the rules of the system.
So I guess the only downside of this approach is that you do have to pay the L1 costs for the transaction to be able to do this.
Right. So the L1 cost is going to be higher, right? Because like we built this whole system. We built all of the rollup in order to be like, we're not able to do a lot of transactions on layer one. So if a user has to put a transaction on layer one in order to get it processed, that's kind of defeats the whole purpose, right? So what we can do, but there's ways for us to mitigate this. And basically what we do to mitigate this is instead of putting a transaction here, the user can produce a ZKP. The user says, okay, I'm done. I'm going to make a ZKP. And they can put the ZKP on chain. And this would be like a representation of many other transactions. They can get this transaction from this user or from other users. And it's possible for them to sort of compress these like many transactions together, just like we do with a rollup. So it's possible for the cost of the forced transaction to approach the cost of like a regular rollup block.
Okay, so there is some coordination effort this guy needs to do, but hopefully he will not need to pay the L1 cost if he is able to get enough other people to include into his ZKP, right?
Yes.
Okay.
And this is like some important nuance here is that because transactions are super cheap on layer two and they're really expensive on layer one, if there's like a censorship attack against like a user or a group of users, it can be really difficult for them to withdraw their money because the transactions are just so expensive. Like if I have like 10 cents on a layer 2 and the Ethereum transaction fee is 12 cents, I can never do a forced transaction.
Yeah.
So it's important that we have these mechanisms to force transactions that are as cheap as the layer 1 gas cost, or as the layer 2 gas cost. Otherwise, users can be kind of like trapped inside a rollup by a malicious user, a malicious coordinator, block producer.
Okay. So basically, just to summarize, there are a couple of approaches. One approach is, you kind of have many block producers, or it's decentralized block production to some extent, and that helps you in some ways, but it doesn't prevent the worst case scenario. And the worst case scenario can be prevented by doing this forced transactions when, if all else fails, and then you can go through L1 and do it. And hopefully, the mechanism that you described can make it actually not super costly to do.
Yes, exactly.
Okay.
Yeah.
Makes sense. Now, I think one of the things that is frequently talked about is like, do we actually need to have many? Like, if we have forced transaction mechanism, is there any value to having many block producers? Can we just have one block producer and say that's enough?
So yeah, so this is an interesting trade-off because like if you have a single block producer, you get some other benefits, right? You're able to have different features, like you're able to have that coordinator kind of like give you like a weak promise that they're going to include a transaction, and they can give that to you very quickly. And like that's just really nice UX. Yeah. People who are used to Web 2 just click a button and it says yes. And like we want to have that same user experience for layer 2. And like one way we can do that is if we can have like a single block producer. And like the good news is that like it's possible for us to use a forced transaction and a single coordinator to get approximately the same guarantees. Like we're inheriting the censorship resistance from the forced transaction, and like we're getting some of the like nice benefits of like a centralized processor by just having a single coordinator. So it's also possible to have a system where we can transition between the two systems. We can have a single coordinator where we have these nice properties, and we can also have like another coordinator who appears and says, oh, I want to be a coordinator too. And we can have a system where like they're able, like one coordinator is able to provide the instant finality guarantees, and the other coordinator isn't. Like there's all these different ways that we can build a system that's able to have this kind of like censorship resistance inherited from layer 1.
And I guess you may still want to have, like, as you said, maybe like a backup coordinator or something like that, or maybe people being able to come in, because in case this guy goes down for whatever reason, you don't want to sacrifice the liveness of the system, right?
Exactly.
Okay. Yeah. Makes sense. So we talked about how do we enforce validity, but one of the things that I'm kind of still curious about is this state transition representation. So you do need to put data on chain, and I guess the question, and I think you kind of explained it, but I want to dig deeper into it. Like, is this actually cheaper than like regular transactions? Like, why is this data smaller than what you would go with like regular L1 transactions? Like, how we're able to make this more efficient from data perspective?
Okay, so let me talk about like the difference between the costs of like layer 1 and layer 2. Okay, so let's take a look at like what's included in layer 1 transaction. So layer 1 transaction has a bunch of data associated with it. It's like to, from, amount, and signature. And the layer 2 transaction basically we can do a couple of things. The first, so we have to basically have the same representation, but we can reduce the cost a little bit.
And this is like just this is a simple transaction. We're not talking about smart contracts yet. This is like a very basic like payment transaction.
Yeah, exactly. Yeah, this is very simple. So on layer 1 we have these costs. For the next section I'm going to talk about. Okay, let's do optimistic rollup and ZK-rollup. So let's see what optimistic rollups will do. So optimistic rollups have the same thing. They have to, from, amount, and signature. So the one thing that optimistic rollups can do is they can reduce the size of to, from, and amount, because on layer 1, to, from, and amount are like I think it's like how much is it? How much is a
256 bits at the very
256. Okay, let's say it's 256 bits.
Yeah.
256 bits. From is 256. Amount is 256. Like, although it's like not exact. Amount is 256.
For these purposes, I think it's fine. We can round up or estimate it.
Okay, and signature is much bigger. Let's say it's like 512.
Yeah.
Okay. So this is the size of those. So on layer 2, we're able to reduce this a lot. We can probably put this down to like 32 bits, 32 bits, 32 bits, and signature is still has to stay the same as 512. 512. Okay, so we're already getting some gains. We're reducing the gas costs by having this like compression algorithm that we're using.
Yep.
Right. So could the layer 1 apply these same optimizations? Could the layer 1 reduce the size of the to address, the from address? And it could. It could. But it wouldn't give any benefit because on layer 1, everyone is executing the computation. And if you reduce the size, they'll need to check that the size reduction was done correctly. So it would just add more computation. So layer 1 has bigger data footprints because execution is expensive. But in optimistic rollups and in ZK-rollups, we have cheaper computation. The computation is very cheap. So we're able to reduce the data size. The next thing to look at, okay, so let's look at ZK-rollup. So ZK-rollup is very similar to optimistic. It's the same to from amount. But it doesn't need a signature. The signature gets removed because the ZKP verifies the signature. In an optimistic rollup, fraud proof verifies the signature. So because we're able to put the ZKP, we're able to replace the ZKP with a signature. We're able to replace the signatures with the ZKP.
So we do need to put a ZKP here, right? But although ZKP gets amortized across all the transaction in a given block, right?
Yeah, we put the ZKP here, which is bigger than one signature, but because the block contains many signatures, it ends up being cheaper. So let me just write up the cost here. So it's 32 bits, 32 bits, and 32 bits for the amount.
And then different proving systems have different sizes for ZKP. Some are very small, right? Like Growth 16, I think, is just cost of a few signatures, probably.
Yeah, yeah. And like Starks are quite big.
Yeah.
Yeah. And so there's different trade-offs there. Like you can have, a Stark can include more transactions though. So like maybe a Stark is going to be better because it's going to have 1,000 transactions. And like there's trade-offs here we need to think about. One other thing to mention is that like it's possible for optimistic rollups to replace this signature scheme. They can use something like BLS signatures instead of the current signature. That BLS is a compressible signature scheme. You can aggregate together many signatures. So it's also possible for optimistic rollup to sort of remove the signature requirement. Yeah.
Would that require like L1 to be able to process the signatures efficiently, or?
Yeah, it would require that, but it's actually possible to do that right now. Like you can do BLS signature verification, and actually theoretically, optimistic rolls would be cheaper than ZK rolls because they wouldn't have to include the ZKP or the signature. But it would be cheaper, but it's very small difference because it turns out we can make ZKPs that include many, many transactions.
One other thing I wanted to ask, so in the tree that you draw previously, like where you had a state, in the context of ZKP, my understanding is that you only need to like put the final state of the, let's say if there are 3 people involved and I send tokens to you and you send tokens to another person, what needs to go on chain is only that I sent 1 token to someone and someone else got the token, but the intermediate transaction doesn't need to be recorded.
So this is a tricky situation because, okay, so what you're saying is technically correct, but like one thing we want to do with blockchains and with Ethereum is to make sure that transactions work once and only once.
Okay.
And there's 2 ways to do this. One of them is that like every time someone makes a transaction, you use a new leaf in the tree, and that means that the old leaf is just kind of discarded and thrown away. The other thing you can do is you can use something called the nonce. And the nonce is just like this number that every time, it's the count of the number of transactions you made. Every time you do another transaction, you increase the nonce by 1. So in the case where you discussed, so let me add this here. So like Ethereum uses a nonce because that makes the tree space. That makes the tree space, like, it allows for the tree space to be used more efficiently.
Yep.
So then, like, you could remove the nonce, but then you would have to make this number bigger. So in general, people use the nonce. But why didn't I put the nonce in the data availability before? Well, we have the nonce in the data availability on layer 1, but on layer 2, we can remove it, right? Because we already have this implicit idea of a nonce, because we have this from. If there's a from, you know you have to increase that nonce by 1. So we're able to remove the nonce here. So like the optimization that you're talking about, it's possible, but it might not work out as being the most efficient thing. Because although you get rid of the nonce and you don't have to put it on chain, you end up like using your state tree less efficiently.
Makes sense. I guess it depends on like what representation, and that's actually maybe a good point. A rollup doesn't need to follow the same state model as the L1. You can experiment with different state models.
Yeah, and some people have done that using like making like a ZK-rollup that's a kind of automatic. What does it AMM stand for?
Automated market maker.
Automated market maker exchange.
Yeah.
Yeah. And this state is completely different.
Yeah. So you can have like an account-based system, you can have a UTXO-based system, or anything in between, or something new.
Exactly. Yeah. There's a lot of space to innovate. And like, there's a lot of things that people are optimizing for that like you might want to optimize for call data size. Maybe you don't care about that. Maybe you want to optimize for like simplicity or something else. There's a big trade-off space with many things to worry about or to care about. Okay.
So basic takeaway, we can compress things, and that's why. So in the previous kind of discussion about validity, we simplified the computation burden, right? Because you don't need to do all the computation in one. Here, we're also simplifying the data burden, so to say, because you can represent things succinctly. But it does seem to me that you only get a constant improvement here, right? It doesn't, like, if you need to put some data, you can only shrink it so much. You can't shrink it exponentially. Am I thinking about it right?
Yes, I think that's correct. So there's more advanced compression algorithms. We are only scratching the surface of like what is possible. That you can have. So there is some interesting thinking here that like theoretically when you put data on chain, you need to put data on chain for new blocks, not for old blocks. So if you wanted to make transactions for, like, if I wanted to send 10 transactions every month to the same people with the same amount, I wouldn't have to put the call data on chain for that. I could just refer to a previous block.
Interesting.
I could just say that, oh, I made this block last week. It's the same block, just this is the same data. So like once data is available, it's possible, but like that's this kind of like nuanced kind of edge case. And I feel like that's like what you're asking is different than that. I mean, that's one thing to be aware of, but in general, so in general, we're moving from a world where computation costs. On layer 1, computation is expensive. On layer 2, computation is like effectively free because we hardly ever execute our fraud proof. And our ZKP is constant time verification. Because of that, like data becomes expensive, and data is a new thing to worry about. And it's impossible to compress data infinitely. You can never just get rid of data.
The other reasons, like you can give up some of the security guarantees to like the Validium model or whatever else. Like it's not a rollup anymore, right? But you can say, I'm not going to put all the data on chain. I'm just going to put roots of the state, and the actual data is somewhere else, like there is something else. But then you don't inherit quite the same security guarantees anymore. Is that right?
You don't inherit, like a Validium doesn't inherit the security guarantees of Ethereum. It affects the data availability guarantees, which like also ends up affecting the validity guarantee. Oh no, it doesn't. Does it affect the guarantees? Not really, but like so it affects the data availability guarantees. So it means that like users can lose access to their funds, and like a malicious coordinator could use that in order to extract a ransom or extract high fees from their users. So like you mentioned that like, okay, there's this problem of data availability. Like how can we scale past that?
Yeah.
So like the kind of like after the merge in Ethereum, the next major feature to add is IP 4844. And IP 4844 basically adds a lot more call data. An Ethereum block right now, I think, includes order of kilobytes per second of data. And IP 4844 will be like 1 megabyte per second, or 1 to 16 megabytes per second. So it's going to be this major scalability upgrade.
Okay.
Yeah.
And in the long term, like sharding and things like that will unlock even more. Is that?
Yeah. So like, yeah, that's true. But like the sharding has changed so much from when it was originally defined, because sharding used to be like, oh, we'll just have like many people executing different things. But now sharding is just like, oh, we're just data availability for many different people.
Makes sense. It's kind of like data sharding, not execution sharding anymore, right?
Yeah.
Okay. Makes sense. Okay. So we talked about fairly simple model for the rollups where this is just moving, some amounts of tokens or whatever, coins from one account to another. What other types of rollups are there? Assuming let's say we want to do something as sophisticated as we can do in an L1.
So we can have a ZK-rollup that supports the Ethereum virtual machine.
Yeah. So it's more kind of like a general purpose rollup, not just a specialized rollup that does only transactions.
Yep.
Okay.
Yeah. So let's talk about how that works. So in order to talk about how that works, first we need to talk about like how Ethereum works. So let me clear this and we can talk about it.
All right. So we talked about fairly simple rollups where you just transfer tokens from one account to another. But obviously we get a lot of like with L1, we get the ability to write smart contracts and like build custom logic and all of the cool stuff. Can we do something similar in a rollup context?
Yes, we can. So it's possible to do that with optimistic rollups. I think Optimism and Arbitrum both have like optimistic rollups that are like EVM compatible. And it's also possible to do that with ZK-rollups, but it's a little bit more difficult.
Why is it more difficult?
That's a good question. Why is it more difficult? Well, okay, let's look at the rollups we talked about before. That like when we were talking about the rollups before, we had like a Merkle tree, and like we did a very simple state transition, where we just like this leaf and this leaf, we updated them. So basically, we just like changed two things. And we did the state transition, and it was easy to make a ZKP for that.
The computation involved here is very easy, and it's fairly simple to put a ZKP together that can prove that computation.
Yeah. The key is that the change is not dynamic; it's constant. Like, okay, we did one state transition here. We're going to do another one where we change another two leaves. And like what we're doing is the same all the time. We're just changing two leaves. We're just updating two leaves. And like because we're doing a constant thing all the time, it's easy. And like we can make application specific rollups that you mentioned earlier. Like we can make an automatic market maker rollup where like we're doing like what Uniswap does, but we manage to encode that in a way that's like just updating several leaves, just changing several things.
The logic is fixed, basically.
The logic is fixed.
Yeah.
And the problem with the EVM is that the logic is dynamic. I can deploy a smart contract that does anything I want. And like if we want to make a ZKP for that, we can, we want to make a proof about that, we need to like dynamically adjust. So there's all these different kind of approaches and mitigations that people have taken to try to allow you to have smart contracts. Like the simplest thing to do is that like to say that, okay, every time I deploy a smart contract, I'm going to make a new ZKP, right? I have one ZKP for this, and I'm going to make a new one for AMM. And I'm going to make another one for something else for ENS. But this is hard to do. It means you have to do like a whole bunch of different setup phases. It means that like you have to update your smart contracts with the new proving keys. It just becomes really difficult to do.
And I would say also a person who deploys it actually needs to be able to write ZKPs, right?
Right.
They need to have the special expertise, which is slightly more complicated than writing Solidity smart contracts, I would say.
Bobbin is being very humble. Yeah, it's a lot more complicated than I think than Solidity contracts, because Solidity contracts are like a paradigm that people already understand. With Solidity smart contracts, you're just doing like, oh, check signature and add this money to this and subtract this money. But with ZKPs, you're not able to do these things. All you're able to do is just like A plus B equal C. You're just able to check that like different numbers are that like there's this constraint between these numbers. And like you eventually use this to compose like a signature check or like other things, but like it's really hard to do. And it's not a good developer experience, especially for like the, I don't know, is it millions or tens of thousands or thousands of people writing smart contracts? Like for the people writing smart contracts, it's really hard. And like one thing that we think about when we think about like, oh, how can we scale Ethereum is like developer experience. But like this is like a mistake that a bunch of people made. Originally, people thought that like, oh, I'm just going to build my thing and people are going to just come and use it. But they didn't really take into account that like it takes a long time to teach people how to use a new thing. So
and the learning curve here is probably super high. And
yeah. So this is one approach. Let's talk about some other approaches because I don't want to spend too much time on this. So this is one approach to just make like specialist ZKPs. Another approach. Let's talk about the compiler approach. Oh, I'm going to leave that there actually because this is ENS. So like we have a system where we have a smart contract for AMM. This is a smart contract, and we have one for ENS. This is a smart contract too. And like basically we say that, okay, well, let's just make a compiler that compiles them across. Yeah, let's make a compiler that converts this into this. And like this works too, but there's some concerns here. Some of the concerns are the compiler security is very difficult to be sure about. That like we have this compiler here that's converting one thing to another. How do we know that it converts exactly the same? The other thing is that like this smart contract is written with like a certain set of security assumptions in mind. But moving to a different execution environment like a ZKP, those security assumptions can change. That's the second concern here. That like people are very worried about like compiler-based approaches because like this could be an issue. There's another approach that just says, let's make a special ZKP and compiler, and like let's not use Solidity. Like in this example I was talking about, this was like Solidity contracts. But yeah, this was in this example.
But I also think making a compiler that compiles arbitrary Solidity is probably a challenging task in itself.
Yeah, it's not easy. I think the complexity approaches the complexity of the zkEVM. But yeah, it's not easy. So those are two types. Let's talk about like the third type, where you're really starting to get close. And like basically the third type is where you figure out a whole bunch of the problems related to the zkEVM, and you say that like, okay, well, what's in Ethereum? So there's stack, there's bytecode,
memory.
Memory.
Storage or something.
Storage. And you say that, okay, I'm going to figure out some of these things, but not all of them. So stack, let's do it. Bytecode, good. Memory, good. Storage, no. Storage is more difficult. So like there's some approaches that kind of basically take storage and like they take the storage tree that Ethereum currently uses and they move to another one. They have a different kind of storage tree. Maybe it's different, like, let me draw it the way that you draw it. I like the way that you draw them, like, okay, like this. So we move to a different like storage structure.
And so to be clear, in this approach, we have a ZKP that will actually prove the execution of the EVM, and we're then making compromises on different parts of the EVM of how we want to represent them.
Yeah, exactly.
I guess one of the curious things, why is storage, for example, difficult? Like, why would we want to change from Ethereum storage to something else?
Right. So storage is different for two reasons. The first reason is that the hash function that the storage uses is very difficult to implement in Snark. It's not that it's difficult. It's that it's just, and it's not that it's expensive either. It's that it's just used so much that the hash function in storage is just used all the time. So like people used to think it was prohibitively expensive. I don't think that anymore.
Yeah.
Yeah. So there's some really interesting work about optimizing Ketchak and things like that. That's really exciting stuff. So that's one of the reasons. The other major reason is that like this representation of state is very complicated. Like this is called a Merkle-Patricia tree, and it's really hard. It's really hard to implement, and it's especially really hard to implement inside ZKP.
Yeah. Inside ZKPs, generally, like the simpler the computation, the easier it is to handle in the ZKP. Something that has a lot of edge cases and complex is difficult to handle.
Yeah, exactly. Yeah, there's a lot of edge cases. Yeah. So this is another approach, and the final approach is basically to just be like, okay, we're going to do it anyway. Is to just be like, okay, we're going to figure out storage. So like, why would people go to this length? Well, like one of the problems with not having storage is that like the philosophy here is basically that if you change anything in Ethereum, it has like these huge implications for other parts of the stack. For example, if you change storage, your deposit and withdrawals are broken. Also, there's a whole bunch of smart contracts that use storage to look up other things. And like if you do that, you'll break those contracts too. So the idea is that like, okay, well, we want to have storage as well. So like, let's make a ZKP for storage as well. And like, we're working on this. A whole bunch of different people are working on this, and we're thinking it's possible. It's just going to take a little bit longer. I think that like the key realization here was to just be like, proof of time doesn't matter that much. That like developer experience is more important than proof of time.
And I think this ties back to like, I think there was a blog post by Vitalik about different types of ZK-EVM compatibility, right? So like, when you handle everything, this is, I believe, like type 1. You basically don't change anything about how EVM or Ethereum work. And then there's like type 2 and type 3, and which are kind of different levels of kind of pick and choose, like what you keep the same and what you change, right?
Yeah.
And then type 4 is like a different one where you just like are compatible at solidity level. Am I?
Yeah, that's right.
Okay.
Yeah. So like, another point of doing the highest level of compatibility is it will let us make a proof of validity for Ethereum. So far today, we've talked about like using ZKPs for state transitions. And like we talked about how layer 1, everyone was checking. And like the idea is that we can have a ZKP so everyone doesn't need to check. And especially people who have like not powerful devices don't need to check or don't need to download so much data. So that's another like really interesting possibility. If we end up with like a single ZK-rollup or a single EVM compatible rollup, then we're able to make this proof of validity. But if we manage to get multiple, then we're able to have like multiple client diversity of different proofs of validity for Ethereum.
Makes sense. Yeah. No, this is like the type 1 ZK-EVM like equivalent. So that basically you can prove the state transition of the main chain of Ethereum.
Yeah.
Okay, awesome. I think one other thing I want to kind of get a bit more detail about, like we mentioned that it's difficult to build ZK-EVMs and zkEVM in general. Like what are the difficulties? Like we mentioned like hash functions being different or like the tree structures being different. Like are there any other like challenges that you faced or others are facing in building this?
Yeah, so like there's a whole bunch of challenges and there's a lot of really fun stuff. Let me talk about one really fun thing, and let me talk also about like the actual difficult challenges.
Okay.
So the actual difficult challenges is like the issue is that like, everything is dynamic. That like we have the bytecode circuit here, and like we're going through our bytecode circuit and we're executing things, and every time we execute something, we don't know where we're gonna go next. Like once we're here, we could go here, but we also could go like to here. Like we don't know where we're gonna go.
Yeah.
And because of that, it's just really hard to get a ZKP to represent that within a ZKP. Because like a ZKP is like just ordered. It just goes like one step at a time, like here. Just update this leaf, update this leaf, update this leaf, update this leaf. But here you can't do that because you don't know what leaf you're gonna do and you don't know like where you're gonna go. That's one of the indications of it. The other difficult thing is that like each time, like not only do you not know where you're gonna go, you don't know. Not only do you not know where you're gonna go, you don't know what you're gonna do. Like if you come here, you're gonna do one thing. You're gonna do like Ketchak, and if you come here, you're gonna check the storage. Like because you don't know what you're gonna do, it ends up that like that like it's just really difficult to have a list of everything that you need to do, because Ethereum has a whole bunch of different opcodes that are like really expensive or really difficult to implement on Snark. So yeah, it's a really fun challenge.
And I think this like difference, by the way, you mentioned like some things are more expensive, but like also in the gas model, right? Like some things are fairly cheap, like Ketchak could be cheap in Ethereum, more or less, and it's an expensive thing in a ZKP context. So like you need to somehow account for the differences, because like if you want to execute 1,000 of Ketchaks, maybe it's fine in the ZKP context, but here it's going to be much more costly. So there's a cost discrepancy between ZKP and the gas model of Ethereum as well.
Yeah. So like that's an interesting question, and it's an interesting topic to think about. Like my opinion here is that like compatibility is so important that like you shouldn't even change the gas prices. You should just be like, prover, you just have to do 100 times more work, and we have to spend 100 times more money on AWS. And like I think that that's okay, because like we're good at scaling compute. Like compute is like we have supercomputers. We've been doing computation for hundreds of years.
Yeah.
That like being able to, I think that it's easier for us to solve that problem than it is to solve the problem of like teaching 10,000 people that this doesn't cost this doesn't cost 10 anymore. It costs 100 now.
Yep. But this is like an example of a challenges like which are not obvious, but still like you need to deal and figure out how you make sure that your execution trace doesn't run out or something like that while doing something expensive while it was cheaper in a kind of original smart contract.
Yeah. Let me tell you about the fun one.
Yeah.
So there's one special opcode that's called extcodesize, and basically extcodesize, you give it an Ethereum address, it will go and get you the size of that Ethereum address, and it will give it back to you. And like this originally was like, I thought that was easy, right? Because we just go to storage, we just look up the contract, we get the size. But like it turns out that like in storage, they don't store the size. They don't store the size of the contract. So when you go there, you can't get the size. So what you end up having to do, you have to go there, you have to get the code hash, and then you have to like get all of the code, hash it together, make sure it equals the code, make sure it matches the code hash, and then you get the size of the code that you put there. So it's this huge amount of hashing. It's like one of the most expensive things in the EVM.
Yeah.
But there's a bunch of approaches to solve it. Like one approach is to put it into the Merkle Patricia tree, to just add the size here. But like that changes Ethereum. Yes. Like what else can we, like the actual solution to this is we're going to have a hard fork to include that. We're going to update the state tree to include the code size, because zkEVM is a really important thing to do.
Yeah.
The other thing we could do is we could just reduce the cost of Ketchak so much that it's okay to have that, because Xcode size is like 100 gas, and like the biggest contract I think is order of kilobytes, so it's a lot. It's a lot of hashing. Yeah. But that's fun. Yeah.
Awesome. Yeah. No, it's a lot of interesting challenges, but a lot of people are working on it. A lot of smart people.
Yeah. I'm really excited to see, like, there's a whole community of different people working on the ZKVM. There's Polygon Hermits. You're working on it too, and like there's other groups. There's Scroll. There's Aztec. Oh no, Aztec or not, but there's Starkware, and there's Matter Labs.
Yep.
Yeah, and there's a whole bunch of optimistic rollups too, and they're all working on this stuff together. And like I think that like at the end, the most efficient solution will be combining the implementations of different groups. Like I think that like I want to be part of a rollup where there's a ZKP, but there's also a fraud proof, and there's a ZKP from Polygon Hermits, but there's also a ZKP from Scroll Tech, and there's also a ZKP from Starkware, and all of these things are checking the same thing, and like this will give you the security guarantees that we really need. Because like with Ethereum, we have this philosophy, we want to have multiple different client implementations.
Yeah.
And when you have multiple different client implementations, it basically says that, well, if one of the clients is broken, I'll just continue, like the other client will recognize it, and no one will be able to be tricked. We'll be able to fix the other client. Yeah. So like we need to have that too for rollups. Yeah, we need to have client diversity, and we need to have fraud proofs and ZKPs, and we need to have like all different groups working together.
Yeah, no, agreed. All right, well, this has been awesome, but just to summarize, like, what are the ZK-rollups and what are the benefits? Like, why do we care of them?
Sure. So rollups are a way to scale Ethereum.
Yeah.
Basically, we use fraud proofs or ZKPs to remove the computation burden. that allows us to worry more about the call data burden, which we're currently compressing. And in the future, we'll have 15 or 4844 will allow us to have like many orders of magnitude more transactions per second. That's what rollups are, and that's like the plan to get to the rollup centric roadmap, where Ethereum is just rollups and everything else is just about data availability.
I think the rollup model also allows you to experiment more and like have faster transaction confirmation and all of that stuff.
Yeah.
Because there are different models that you can deploy where, you still inherit the same security, but you can, let's say, for short term, you trust in optimistic way for a centralized validator or something like that, right?
Yeah. I found a group working on ZK-WASM. We could have a ZK-WASM rollup in the future.
Yeah.
That could be fun.
Yeah. Awesome. Well, thank you so much, Barry.
Yeah, thank you, Bobbin. Yeah, happy to help.
Yeah. Thank you, everyone.